has told us about quite a few techniques which relate spectroscopic measurements to cyclic voltammetry. This technique, which I will talk about, also relates spectroscopic measurements to non-stationary states of the cyclic voltammogram, but the whole technique is electrochemical. All measurements are done by electrochemical means. First, I will talk a little about some basics, very simple things about impedance spectroscopy, avoiding any mathematics. In fact, books on impedance spectroscopy are too overloaded with mathematics, and this fears users. But with present-day software, users do not need all those Laplace transforms and all the mathematical stuff to use impedance spectroscopy. But what is really important on the user level is the understanding of how objects in electrochemical system relate to objects in electric circuits. And great errors in literature are made on that physical basis of relating different electrochemical objects to circuit elements. And when we talk about objects of impedance spectroscopy, it is important that they are somewhat specific, so that the object can be either a component of the electrochemical system, such as the double electric layer or space charge layer in a semiconductor. And the objects can be also processes. Diffusion and charge transfer across the interface are also objects of electrochemical impedance spectroscopy. This dualism has to be kept in mind when talking about objects of electrochemical impedance spectroscopy. And when we relate those objects to circuit elements, the concept of equivalent circuit is important. I will give some equivalent circuits. And classical impedance spectroscopy is a stationary technique, and it uses the assumption of stationarity already in the measurements. So not only the conclusions, but even the data can be incorrect when people apply stationary impedance spectroscopy to non-stationary systems. I will also talk about this problem of non-stationarity and how what problems arise and how they are overcome by non-stationary impedance spectroscopy with a technique which introduces the concept of potential dynamic profiles. In cyclic voltammetry, electrochemists deal with potential dynamic profiles of the current. And those potential dynamic profiles characterize the system as a whole. In impedance spectroscopy, when we use it in the potential dynamic mode, we also obtain some potential dynamic profiles, but they are related not to the whole system, but to some objects which are analyzed by electrochemical impedance spectroscopy. And I will show those potential dynamic profiles for different objects, and also will pay some time to problems which arise in literature with interpretation of circuit elements, and some errors are widespread in this field. When we come from direct current to alternating current, or in general to the variable current which originates in the variable potential, then we have to use more than one variable to describe the response. Not only the amplitude of the signal is important, but also the phase. In some objects, the current may lead the variation of the potential, and in other systems, the current may lag the variation of the potential. And this phase shift on the time scale is also an important parameter of the object. Correspondingly to these two parameters which are required to characterize the response, the relation between voltage and the current in the circuits of direct current, which is related by the resistance, transforms into something different, which is called impedance. Impedance is the two-dimensional analog of the resistance in the circuits when the variable potential causes the variable current. One more complex things in impedance spectroscopy is the use of real and imaginary impedance. People often consider imaginary impedance as something unreal, but the use of complex numbers in impedance spectroscopy is just the mathematical approach how to present two-dimensional values. They are presented by complex numbers which have real and imaginary part of impedance. When the circuit contains just the objects that dissipate energy without shifting the phase, they have only a real part of impedance, and the whole impedance is equal to its real part and to resistance of the system. The other kind of the systems may have only imaginary part. For example, capacitance has only the imaginary capacitance. In Cartesian coordinates, this is presented by horizontal axis real part of impedance, and vertical axis is the imaginary part of impedance. And normally electrochemical system has both the real and imaginary part of impedance. And the inverse value of the impedance is called admittance. And both the impedance and admittance sometimes are called emittance. Emittance is a general name for both the impedance and admittance. This table shows the very simple basic elements which have impedance only as a part of real or imaginary impedance. Resistors have only a real part of impedance, and capacitors and induction coils have only imaginary impedance, but electrochemical system has complex impedance of both real and imaginary parts. And the response of any object to alternating current, or in general to the variation of the potential, is dependent on frequency. So in impedance spectroscopy we have a frequency dependence of a two-dimensional value, because the value itself is two-dimensional and it is analyzed on the frequency scale. The signal is very informative, and the problem is how to extract this information from the signal that potentially has much information. Already on the level of raw data, when we consider variations of components of impedance, for example, in this figure, which is taken from the December issue of Electrochemical Acta, where we investigated cadmium electrodeposition on cadmium selenide quantum dot electrodes. The figure presents a variation of imaginary impedance for 10 frequencies in cyclic potential scan. Different colors refers to different direction of the scan shown by the arrows. And cyclic voltammogram is also given for reference here. There are two processes of cadmium reduction. This one is the underpotential deposition. Professor Lapkovsky also told us about this phenomenon of the two reduction and oxidation processes. One is related to the adsorbed state. Here is the adsorbed state of cadmium on cadmium selenide, and it was interesting that it depends on the size of the of cadmium selenide quantum dots, and actually that article was about the size effects. But here I want just to show how the potential dynamic profiles of components of impedance may give already in raw data some information about the object. This figure shows the variation of the phase shift in this system. When the potential is scanned, we see that the phase shift also shows us some changes in the ranges of corresponding electrochemical processes. When the electrochemical absorption proceeds, when the nucleation proceeds, and finally when the cadmium nuclei are anodically oxidized. We here see all the structures. So some information can be observed already in the raw data of a real imaginary impedance, phase shift, and also in this case impedance modulus. This is also from the latest publication from Russian electrochemistry, from the latest issue. And in this case, it is interesting that the phase shift and the impedance and the imaginary impedance show very similar patterns in cyclic scans. And this is because in the region of almost zero current, impedance is almost entirely imaginary. So the imaginary impedance characterizes what happens on the interface, and we see some significant difference in the forward and potential scans, which is due to variation of the interface capacitance, dynamic variation, which is not stationary. And from this variation in the system, in platinum, in concentrated lithium chloride, we investigated formation of ion pairs on the interface. Impedance spectra can be presented in different ways. I will show this using our software. This is EIS spectrum analyzer. It's a rather user-free software for simulation impedance spectra and for the analysis, and it can be downloaded free from our web page in Belarusian State University. So the impedance spectrum, if we consider it for the simplest circuit, just one capacitor and just resistor, and just one resistor connected in parallel, it can be presented both as the dependence of imaginary impedance on the real impedance, or explicitly as frequency dependencies of impedance modulus or the phase shift. These two plots form a pair of Bode plots, and impedance spectra can be presented as a pair of these explicit dependencies on the frequency, or as a Nyquist plot, which presents the frequency dependence implicitly. Each point corresponds to different frequency in Nyquist plot, and here is the highest frequency, and here is the lowest frequency, and the frequencies are scanned here implicitly, unlike the same information, just with a different presentation. When we talk about impedance spectra of electrochemical systems, a very important point is the presentation of various components of electrochemical response by circuit elements, by the elements of electric circuits. And this is not just because of the models, but there are electrochemical objects which correspond really to simple circuit elements. For example, charge transfer resistance, which characterizes electrochemical kinetics, is just a resistor. It is represented in impedance spectroscopy just by the active part of impedance, real part of impedance. Adsorption resistance is also a resistor. So if we consider the response in terms of equivalent circuits, it will be just some resistor in the equivalent circuit. And they are both parameters of kinetics. Resistance of solution is a simple resistor. Capacitors are double electric layer capacitance, which characterizes the state of the interface. Capacitance of adsorption, which relates to kinetics of adsorption, and surface and capacitance of surface space charge layer in semiconductor materials is also a typical capacitance which is considered in impedance spectroscopy. A very important parameter in investigation of semiconductors, because the square of inverse value dependence on the potential gives a Mott-Schottky plot, the plot which is important for characterization of semiconductors for doping level and also for flatbed potential, which gives the position of the energy levels corresponding to the electrochemical scale. And Professor Lapkovsky has told us about this problem, how to relate the two scales. And when we measure Mott-Schottky plots from space charge layer dependence on the potential, this information is obtained about semiconductor, which helps to relate the energy levels with the electrochemical scale and to characterize the doping density of the semiconductor. In the simplest equivalent circuit of an electrochemical system, there are at least double layer capacitance. There is also some double electric layer at the electrochemical interface, so this capacitance is usually present. However, sometimes frequency response analysis gives, instead of double layer capacitance, the constant phase element, which is the analog of the capacitor, but in the formula of the frequency dependence of the impedance on the instead of the capacitance, there is another parameter in the power which differs from one as the capacitor has. So it can be treated as a distorted capacitor until the exponent of the constant phase element is very close to 1, that is the impedance of that element is very close to the impedance of a capacitor. But for perfect surfaces, impedance spectroscopy usually gives capacitor. But when the surface is distorted, it may give a constant phase element instead of the double layer capacitor. Charge transfer resistance is a kinetic parameter which characterizes how fast the reaction proceeds. It is directly related to rate constant. And mass transport of the electroactive components of the electrolyte is represented by impedance of diffusion. Impedance of diffusion can be either simple with one parameter when linear semi-infinite diffusion is considered. That is, the surface of electrode is flat and there is no limitation for diffusion in the solution. But when the surface is not flat, when it is curved, or there is some limitation for diffusion, for example, when the impedance spectrum is measured on rotating disk electrodes, then we have just a controllable thing layer for diffusion on the surface. Then this simple Warburg element transforms into more complex elements with more than one parameters. So it can be either used as predefined in the analysis or can be simulated from theory, the dependence of impedance of this part of electrochemical circuit on frequency. Most complications which arise in literature about analysis of electrochemical system response in terms of electric circuits concerns the capacitance which can sometimes appear in the Faradaic branch of the circuit. This capacitance is usually called pseudo-capacitance to distinguish it from the true capacitance of the double layer. And I will show further how this and why this capacitance can appear or not appear in the analysis of a response of the electrochemical system. Sometimes adsorption can show up by a pair of resistors and capacitors in the equivalent circuit. For example, when atomic layers are formed, metallic atomic layers in the underpotential deposition with strong effect of anion adsorption. Then the two adsorption processes have two different kinetics which can be resolved by two parts of the equivalent circuit. The common impedance spectroscopy is a stationary technique, and it was historically this stationary technique, but not all objects can be investigated in stationary states. If we consider, for example, electrochemical adsorption of this kind, as this is also from our latest publication, under potential deposition of lead on bismuth telluride. So if bismuth telluride electrode is cycled in the solution which contains lead cations, there are two cathodic processes, the underpotential deposition, then the nucleation. Here is the cathodic reduction of ions, which corresponds to formation of lead nuclei, and here the metallic nuclei are oxidized, and the monolayer of lead is oxidized at much higher potential. But these peaks can be observed only in cyclic scan. If we consider stationary impedance spectroscopy, the stationary current here is zero, and here the stationary current is also zero. So if one uses stationary methods for characterizing these kinetics, there will be no kinetics and no parameters of kinetics. Impedance spectra will be measured in this range of potentials, but they will not contain any kinetic information about this process because the rate of the process is zero. How to overcome this? How to investigate with impedance spectroscopy this system and characterize its kinetics? Non-stationary impedance spectroscopy solves this problem and gives the possibility to characterize non-stationary systems with equivalent circuit and analyze their parameters. And for example, in this system with UPD of lead on bismuth telluride, non-stationary potential dynamic electrochemical impedance spectroscopy gives a characteristic peak of inverse charge transfer resistance, which cannot be observed in stationary state because in stationary state we see no kinetics of the process. But when we scan the same way as in cyclic voltammetry and measure impedance spectra along the potential, then this dependence can be observed. Potential dynamic electrochemical impedance spectroscopy combines the two very different approaches. The approach of impedance spectroscopy, which is normally a stationary technique, and the approach of cyclic voltammetry, which is a potentially dynamic technique. Both approaches have some advantages and disadvantages, and potentially dynamic electrochemical impedance spectroscopy tries to merge the benefit of the both approaches so that frequency response can be analyzed instead of just a current in the potential scan, and comparing with stationary impedance spectroscopy, it analyzes variable dynamic systems and those objects which can be observed only in the dynamic states. The simple two-dimensional plot here is just an example of a Nyquist plot, the dependence of imaginary impedance on real impedance, and the other kind of two-dimensional plots, the dependence on the potential of the current in cyclic voltammetry. These two approaches give a three-dimensional plot in which the impedance spectrum, the dependence, again, the dependence of imaginary impedance on real impedance, they just shown in different cases by different symbols, either Z real or Z prime with relation for the imaginary and real components of impedance. So the spectrum is scanned along the potential in two directions, and we have, instead of a curve, a cyclic voltammetry curve, we have the variation of the two, we have the two surfaces. One corresponds to impedance spectra scanned along the potential in one direction, and the other in the opposite direction. This can be done both for Nyquist plot and Bode plots. In the case of Nyquist plot, the normal coordinates of impedance spectroscopy of the Nyquist plot are extended to the variable potential by the third dimension, and the spectrum is scanned in both directions along the potential. And current is also measured in the same potential scan, so cyclic voltammetry is also present for reference when potentially dynamic electrochemical impedance spectrum is recorded. The spectrum is recorded at very small steps, usually one, maximum two potential steps, so that the scan can be almost quasi-linear. Because the technique is potentially dynamic, we cannot measure the whole impedance spectrum. It would take too much time. So the part of impedance spectrum is usually taken which contains most important information. For example, in this case, it was very narrow potential range, but the inexpressive spectrum, two-dimensional, transforms into some pattern in three dimensions when the variable potential is added. This is the three-dimensional extension of the Bode plot. Historically, fast electrochemical impedance measurements started in the 1970s from the works of Smith, Bond, and other people who used at that time those big computers, small programs on big computers, to measure impedance fast enough. And presently, methods are much more different, but the ideas were laid already in the 70s of the 20th century of how to do this fast enough to investigate non-stationary systems. This diagram shows the potential dynamic impedance spectroscopy in principle, how it works. The program on a computer interacts with the three electrode cell by a potentiostat, as in any electrochemical technique, and the whole work is done by the software which scans the potential and which processes the data and forms such impedance spectra in three dimensions with a scan of the potential. The form of this spectrum can give some information already in this raw data. For example, here forward and backward scans are shown in different color, and it is directly in the from the spectra it can be observed that in some potential range the system is more reversible than in the other potential range. Here the spectra are very different because the system goes through different states in forward and backward scans. So the advantage of the potential dynamic techniques, also of cyclic voltammetry, is that it can compare at the same potential different states in the forward and in the backward scans. And the spectrometer gives the Nyquist plots and Baudet plots, which are changing at each step at one or two potential steps in the potential scan. The typical scan rates are usually within 10 millivolts because the time is required to acquire impedance spectrum. Here some examples are shown for impedance spectra of objects which differ in their reversibility. For perfectly reversible system, the forward and backward scans give somewhat similar spectra. For entirely irreversible systems, they are quite different, and there are also intermediate situations when in certain ranges of potential the system goes through similar states in forward and backward scans, and in other ranges of the potential they go through very different states. So the system can be entirely irreversible, locally irreversible, or reversible. I will use many examples about underpotential deposition, because underpotential deposition is one of those processes which benefits mostly from using the non-stationary approach. Some other systems can be investigated both by stationary and non-stationary approaches, but when the especially irreversible adsorption is considered, then the kinetics of the process can be measured only in the non-stationary state. So first we observe just the raw data, such three-dimensional plots of impedance spectra, which can give some information, but it is just a qualitative information. In order to obtain quantitative information, we analyze those three-dimensional plots in terms of equivalent circuits using the same approaches as are used in classical stationary impedance spectroscopy, but with some sophisticated software which analyzes hundreds and thousands of impedance spectra at the same time, because if we consider 1 millivolt step, so for the volt range there will be 1,000 of spectra. So by normal routines this will be too hard work, and this is overcome also by software methods. For simple reversible systems, for example, this redox system, the equivalent circuit is a Randall circuit with double layer capacitance, charge transfer resistance, impedance of diffusion, and the potential dynamic impedance spectroscopy gives not just the values of those parameters, but it gives the potential dynamic profiles. So we see how, for example, Warburg constant depends on the potential in the potential scan. It forms the inverse value as a function of the potential, gives such a peak at the potential of the corresponding electrochemical reaction. When the components of the electrochemical response are separated, then it can be easily observed that different factors affect different components of the electrochemical response. These two dependencies of the inverse charge transfer resistance and the Warburg constant of that system in the potential scan show the effect of thioglycerol adsorption correspondingly on the parameter which characterizes mass transport and on the parameter which characterizes charge transfer across the interface. And in this case, the effect is much stronger, and it is clear. Why? Because the adsorption strongly affects kinetics, but not so much it affects the mass transport. Yes, and here some equations are shown. I tried to avoid mathematics, but some important data is presented. These parameters which are extracted from impedance spectra are related correspondingly to this one to diffusion, to coefficient of diffusion, and this one to kinetics of electrochemical reaction. So from this information, normal parameters of which are used in electrochemistry can be always extracted. Now, very important point about the difference of responses in alternating current and the corresponding parameters of the circuits for not only reversible EPD, any reversible electrochemical adsorption. Professor Lapkovsky already gave this kind of cyclic tomograms for reversible adsorption, which when cathodic and anodic peaks strongly overlap, the process is very reversible, but it can be also irreversible. Then the cathodic and anodic currents do not overlap on the potential scan. In this case, at the same potential, reaction can proceed in both directions, and in this case, at the potential of the cathodic peak, only cathodic reaction can proceed, and at the potential of anodic peak, only the anodic reaction can proceed. And this affects drastically the equivalent circuits of those systems, whether the cathodic and anodic currents proceed in the same potential range or they proceed in the different potential range, because the adsorption capacitance originates in the oscillation of the atom coverage. So if the alternating current can cause the oscillation of the atom coverage, then the adsorption capacitance appears in the equivalent circuit. If the atom coverage cannot oscillate, that is when the cathodic and anodic peaks on the cyclic voltommogram do not overlap, there is no this term of the response, and correspondingly there is no adsorption capacitance in the equivalent circuit. But you may find hundreds. We have estimated even up to 1,000 publications in literature about derivation of great capacitances in the Faradaic branch for systems with not overlapping cathodic and anodic currents. So people just integrate the current and attribute the current to the capacitance. But in fact, in such systems, the current flows through this dissipative branch. And the capacitor is the element of the circuit which can store energy in electric field. And this part of the circuit just dissipates the energy. It doesn't store energy. So in this kind of equivalent circuits, in objects which correspond to this kind of equivalent circuit, the current is mainly the Faradaic non-capacitive current. So no integration of this current should be attributed to the calculation of capacitance. If the capacitance is present in an electrochemical system, it can be first observed in the type of cyclic voltammetry and confirmed by frequency response analysis, which gives this capacitance of adsorption in the Faradaic branch. Only in the case when atom coverage can oscillate with the perturbation of the potential, only for such systems the adsorption capacitance is obtained by frequency response analysis, by analysis of the impedance spectra. Here again some examples of different types of electrochemical adsorption, examples with under-potential deposition and corresponding equivalent circuits. There, for any process, the equivalent circuit can be different, so one knows beforehand, doesn't know beforehand what equivalent circuit can be in that in that particular system, and this is the job of the analysis of impedance spectra. The software helps to derive these circuits and to obtain parameters of those circuits and consider them as functions of the variable potential. In bismuth under potential on gold, the equivalent circuit is rather complex. Two adsorption processes are resolved for this process. In cadmium under potential deposition, the situation is somewhat different when cadmium is deposited on bulk tellurium or on monolayer of tellurium on gold. In the case of bulk tellurium, there is no limitation for diffusion of cadmium. Therefore, the spectrum is much more irreversible than in this one. The diffusion is limited by a single monolayer of tellurium on the surface of gold. Here, the parameters of equivalent circuit of the under-potential deposition of lead on tellurium show how the process can be monitored by potential dynamic electrochemical impedance spectroscopy. Double layer capacitance, which is here somewhat distorted as a constant phase element, but in fact it's almost the double layer capacitance, shows the cyclic variation. It increases about 4 times in the range of add layer deposition on tellurium, of leaded layer deposition. Then with the hysteresis it goes back to the low value of tellurium itself, of the double layer of tellurium. And the variation of this parameter characterizes the status of interface and how the status of interface changes in the cyclic potential scan. And the two other elements, the resistance of solution is the parameter which doesn't depend on the potential. It is not affected by the potential, so it is of no interest. And this one corresponds to charge transfer, characterizes the interfacial charge transfer, and this one characterizes the diffusion of lead cations, which is required for this reaction. And inverse values of the both parameters show peaks which characterize the process. So instead of one parameter observed in cyclic voltammogram, potentially dynamic electrochemical impedance spectroscopy in this case gives 3 potential dynamic profiles which separately characterize different components of electrochemical response. Under potential deposition of lead on gold is an example of perfectly reversible electrochemical adsorption, and correspondingly the equivalent circuit acquires the adsorption capacitance because of the reversibility of this adsorption process. And again, by analyzing various parameters as functions of the potential, separately can be observed the status of the interface, the adsorption capacitance, which gives here a sharp maximum, and this sharp maximum in scanning microscopy, scanning tunneling microscopy, corresponds to a phase transition on the surface, the restructuring of the layer of lead on gold, and the adsorption and the diffusion also is represented separately from impedance spectrum. So first we acquire a three-dimensional impedance spectrum, the dependence of real and imaginary impedance on frequency at each point of the potential scan in both directions, and then this three-dimensional data is analyzed and gives a set of potential dynamic profiles which characterize separately different components of electrochemical response. This example shows how the two circuits can transform from one to other circuit. When lead is deposited, when lead add layer is deposited onto bare gold, the process is perfectly reversible and corresponds to this equivalent circuit. But when an add layer of selenium is deposited on the gold substrate before the underpotential deposition of lead, the cyclical photomegram transforms to much more irreversible photomegram. So at the peak of cathodic current, there is almost no anodic current, and correspondingly at the peak of anodic current, there is almost no cathodic current. And impedance spectroscopy observes no capacitance in this case. So the type of cyclic voltammetry is related to what we can see, whether we can see capacitance or not. And in a great number of articles, this kind of cyclic voltammetry is used for calculation of capacitance from the current, and people obtain very great capacitances for such systems, farads for square centimeter, so unrealistic values. And first such articles were published only in material science journals, but now they penetrate already in electrochemical actor, and a few articles were published in electrochemical actor when people present typical Faradaic response and calculate capacitance from the Faradaic current. So it's not correct, and impedance spectroscopy shows that there is no capacitance. It shows directly that there is no capacitance which corresponds to this type of Faradaic current. Potential dynamic electrochemical impedance spectroscopy helps to monitor assembly of atomic layers. And this slide shows an example of a three-layer structure assembly: tellurium, copper, and lead add layers deposited one after another, and potential dynamic response, impedance response is acquired, and further it is analyzed in terms of equivalent circuits. Though cyclic voltammetry also can give some information, but for example, this peak of copper under potential deposition on tellurium add layer supported by gold corresponds to very inexpressive cyclic voltammegram, but gives very perfect peak in potential dynamic impedance. So when we decompose a complex response into constituents, it becomes much more expressive and helps to monitor the process. A rather complex equivalent circuit for copper under potential deposition on gold, which is affected by co-adsorption of anions. Because of the co-adsorption of anions, impedance spectroscopy resolves two parallel circuits of resistance and capacitance, and these two parallel circuits, when examined as functions of the potential, give those potential dynamic profiles, which show that different anions differently affect different components of the response. Charge transfer resistances and capacitances, adsorption capacitances, and the double layer capacitance. So this approach helps to penetrate into the complex system and look on it from the point of view of components of the electrochemical response. Another process with a similar equivalent circuit is bismuth-rubidium gold It depends rather, it has a rather complex dependence on the potential because a multi-stage process, even in the add layer deposition, and also very complex dependencies on anions. Different anions give different patterns of potential dynamic profiles of this system when potential dynamic impedance spectra are analyzed in terms of equivalent circuit. For investigators of semiconductors, a very important parameter is the charge, is the surface space charge capacitance, space charge layer capacitance. It can be measured by classical impedance spectroscopy, but I have intentionally presented an example in which stationary impedance spectroscopy fails. When titanium dioxide is kept in the range of hydrogen evolution, titanium oxide is doped by hydrogen, and the doping by hydrogen changes the doping level. So if one scans the potential very slowly, there will be no Mott-Schottky plot. So if one acquires the Mott-Schottky plot with stationary impedance spectroscopy, there will be no effect, there will be no such effect of the doping by hydrogen on the slope of the Mott-Schottky plot, which characterizes the doping density. And the equivalent circuit in this case is somewhat abnormal. The capacitance of the space charge layer has something in parallel which looks very much like the Faradaic branch. But in fact, this diffusion is the diffusion of hydrogen, not the diffusion of components of electrolytes. So sometimes impedance spectroscopy gives not what is expected, but what appears interesting, despite that the result is unexpected. But not always the analysis of the spectra can be performed easily in terms of simple circuits. What to do when analysis does not give fit to all the circuits which you try? There are two different possibilities. First, instead of predefined circuit elements, some dependencies, some model dependencies can be used, and our software allows to replace predefined elements by parts of the equivalent circuits which are just formula of impedance. For example, impedance of diffusion depends on size, on sizes and on the curvatures. And this all can be calculated and presented in formula. So when instead of simple Warburg element, the part of the circuit can be replaced by those formula which present the dependence of the impedance on the frequency. And then the analysis goes in its normal way and gives those parameters. Just there will be more than one parameter for diffusion. But even if this approach does not work, raw data can be also sometimes very helpful. For example, this system, or a very simple system, platinum in sulfuric acid, can be resolved in impedance spectroscopy, in potentially dynamic impedance spectroscopy for the non-stationary states, especially by a rather inexpressive circuit element, constant phase element, but not in the place of double layer capacitance, but in the place of but in the part of the Faradaic response, and it cannot be easily interpreted physically what this constant phase element means. But when we consider potential dynamic profiles just of the components of impedance, in this case the phase shift, the variation of the phase shift clearly indicates the oxidation of platinum, in the range of platinum oxidation. So similarly to nanogravimetry or to cyclic voltammetry, the potential dynamic measurements of impedance can be also used in as some raw data which characterizes the processes. One more example, when already the raw data show the complexity of the process. This was an old measurement of the object of Pavel Kulesha, and the impedance spectrum, here the imaginary impedance and a real part of impedance, show the multi-stage transformations of that complex object. Though the analysis of the spectra in terms of equivalent sector was rather complex. With the data obtained from potential dynamic electrochemical impedance spectroscopy, we can perform further various tasks. For example, in this work, the potentials of under potential deposition were derived from profiles of inverse charge transfer resistance. This is the cathodic and anodic profiles of the under potential deposition charge transfer resistance, and they show the potential of UPD and which is not always easily obtained from cyclic voltammetry. And we analyzed some thermodynamic relations of those under potential deposition potentials. It is a published work, but I will not go into details. Concluding, impedance spectroscopy itself as a stationary technique is already a rather powerful technique because it allows to decompose the response of the whole system into parameters which characterize separately different objects, different electrochemical objects, and the objects are either structures or processes at the electrochemical interface. But in a non-stationary system, the stationary impedance spectroscopy fails to give information because the system is stationary and the method is the system is non-stationary, but the method assumes stationarity. Then the non-stationary impedance spectroscopy helps to overcome the limitations of the classical impedance spectroscopy, and it adds a very important thing, the potential dynamic profiles. It gives parameters not just as values, but as dependencies of the potential. Similarly, the difference is similar as the difference between measurement of the current in stationary states and obtained in the cyclic voltammogram. Cyclic voltammogram is much more convenient for analysis of the system than a single value of the currents. The same is for parameters of the impedance which are obtained by analysis of impedance spectra of non-stationary systems. Thank you for your attention.
Thank you very much.